So this is a story about how to find the average value of a function um, if you don't have a lot of calculus tools or if the function is unpleasant to work with. So a brief background, there are two sources of error in the operation of a mechanical machine. So one source is source 1, another is source 2. They're errors in 2 dimension. So you have an error to the right and an error kind of up and to the right in this picture. The total error then will be the vector sum of the two. So r equals s1 plus s2. And the orientation of these two errors is random. So this angle theta is anywhere in between 0 and 2 pi. Now, with a little geometry and trig, I suppose, you can break this second error into a piece that's parallel to error 1 and a piece that's orthogonal to error 1. So the orthogonal piece is opposite the angle, so S2y is S2 sine theta, right? You see how that works? The parallel piece is adjacent to the angle, so S2x over S2 is equal to the cosine of theta. Or you learn to quickly say S2x equals S2 cosine theta. The adjacent piece is the hypotenuse, cosine theta. Now we want to figure out what the total error is. Specifically, on average, how long is it? The Pythagorean theorem allows you to have a long triangle with 3 sides. One of the sides is r, right? That's the hypotenuse. So r squared is like c squared. Another side is this vertical part of s2, so s2y squared. And the bottom of the triangle is s1 plus whatever part of s2 is parallel with s1. So s1 plus s2x squared. So there's a squared, b squared, and c squared. Now, if you work through the algebra, you can show that the length of this radius vector is a squared and b squared and 2ab cosine theta. This is kind of like the law of cosines. Not quite, but it feels similar. Now, this is a radius, an error radius, and it's caused by these two errors. And these errors are both random. And so if you think about this in a manufacturing sense, you could just drill 1,000 holes in 1,000 circuit boards, and then for each circuit board measure how far off the hole is from where you want it to be. It would take some time and be expensive, but it's certainly a measurement technique. So let's do that with Excel. With Excel, you can simulate drilling 1,000 holes. So the first thing you need to do is make a random number. And the random number is going to be in between 0 and 1. And you can do that in Excel by typing RANDOM. No, you can't. RAND. So there's a random number. Now we need to make a random angle. And that angle is going to be between 0 and 2 pi. We'll do that by multiplying our random number. So we type equals the cell times 2 times pi as a function. So now we have a random angle. I'm going to make this a little easier to read. There. So now we have a random number and a random angle. So now we need to figure out what our r value is. Let's start with our r squared. So this will be the magnitude of the radius vector. And to do that, if we go back to our formula, remember we need the first error squared, the second error squared, and then the cross term. So what's the first error in centimeters? Let's say it's 1.2 centimeters. What's the second error in centimeters? Let's say it's 3.1 centimeters. Now we can code in this expression by just typing the formula in Excel. And I'll adjust this so I can switch back and forth less. So we want the first error squared plus the second error squared plus twice the cross term between them times the cosine of the angle that we're operating on. Finally, we can find the average, the absolute value of the length. We do that by just computing square root, of the square of the length. So the square root of 18 is about 4. Notice every time we type, the numbers all change. So I'm going to select these 4 elements. This is one hole in the circuit board that we've just drilled. Let's drill another hole. So I'm going to copy this with Control C, and I'm going to paste it right here with Control V. I don't know why that happened. Control C, Control V. There we go. Now, this looks like a random number. Notice we can check our formula right here. This looks like the random number times the angle. And this, if we click on it, the references are color-coded. This element is broken. I'm not referring anymore to S1 and S2. And so I need to fix my formula. Going back to R squared, what I need to do is I need to lock down the reference. I do that with dollar signs. So if I make dollar signs in front of the cell references that I don't want to move, they're locked down. And then when I copy and paste, look, the cell references are wonderful. See how they're locked down, the red and the blue? But the purple scrolls as the green scrolls. So the green is what I'm working on. The purple is the angle. There it is, the cosine of the angle. It's wonderful. So now we have 2 holes that we've drilled in our circuit board. Let's drill some more. So in a numerical analysis class, this method is called Monte Carlo because it's kind of like rolling dice, and Monte Carlo is a famous casino. So now if we want to say the average value of, this is kind of sloppy syntax. So let's clean up the sheet just a little bit. So the average value of, and let's just average the quantities below. So we'll find the average of all of these elements. So the average value of a random number between 0 and 1, a half, oh, I feel good about that. The average value of a random angle, 0 to 2 pi, is about pi. Notice it's not pi, right? It's 2.9, but that's pretty close to 3.14. So let's just carry this over. So the average value of the magnitude of the radius when S1 is 1 and S2 is 3 is about 3.18. Now, because we used a random number generator, every time I type a new number, anywhere in the cell, our estimate for what the average is will change. But notice that this number clusters around a certain value. If you want a more stable estimate of what that length is, then just roll the dice 1,000 times instead of, just 100. Of course, it takes a long time to get to 1,000. So let's How about this? Let's copy. Oh, let's copy everything we have. Let's go to the bottom. Let's go to the top. Let's copy everything we have. Let's go to the bottom. All right, now we have a whole lot of random numbers. We'll refresh them. And then we'll change our averages so that they're all the numbers. So now we have about 1,700 dice that we've rolled. So now look, that rounds to a half. When we copy and paste across, so our number looks to be about 3.25. And when we type in different numbers, 3.21, 3.19, so I would say this is about 3.2 plus or minus 0.05. That's what I think the average value of R is for this case. This is a really valuable tool because I may not be able to integrate this. Heck, I may not even know how to integrate this yet because I haven't taken Calc 2. But I can still find the average value of this from many different angles. So this is a useful technique.